Hey guys, today we're going to be talking about reversible reactions and chemical equilibrium. To begin, let's talk about a reversible reaction. There are many processes in chemical reactions that are, it's possible they can go in a forward direction or they can be done in a reverse direction. A couple things to think about in biology would be oxygen can bind and then be released from hemoglobin in the body. When you breathe in and you exhale, there are chemical reactions that are taking place, and they're reversible processes. Also, in a physical sense, in the environment, we know that water is going to evaporate away from oceans. It is going to condense then up in the sky, and it's going to rain, so there's a reversible process as well. The carbon cycle, having carbon move back and forth from the atmosphere to the environment through a number of different systems, is another form of reversible process, though that one is much more complex. When we talk about chemistry, we have a few things that we'll talk about as well. One example is when a solid is going to dissolve and then crystallize. If you look to the right here, what you're going to see is we have a series of ions that are in solution, and the majority of them are free-floating. You can see down here we have dissolved particles and bound particles. Well, what just happened here is we dropped some solid into that solution, and you notice that some of those bound particles are separating out away. At the same time, however, some of the particles that were moving around in solution are recollecting on the structure that we have down on the bottom. So that again is our example of a solid crystal that dissolves and then reforms. That is our two-way process. And one branch of chemistry that we deal with is also electron transfer, oxidation, and reduction. And then we have acid-base chemistry, where hydrogen ions are going to go from one chemical to another, and sometimes hydroxide will be a factor there as well. So let's try to dive a little bit deeper in just our understanding of how these things will come together. In the redox form, one of the nice things that's very visible, here we have the example of a cleared out solution. If you shake it, you're introducing oxygen into that clear solution. As you do that, you'll notice that the color changes from being that nice clear solution to sort of a royal blue. This is again a reversible reaction. This blue compound that we have on the right, as oxygen leaves that system, it's going to turn clear again. And then some shaking will remix the oxygen, and that process can go back and forth. Now, one thing that you want to be thinking about is the time frame of a reaction. Okay? In the beginning, we know that reactant concentrations should be very high, product concentrations should be very low or zero. The forward reaction rate should be very high in the beginning. So if we think about that, if I had a molarity versus time curve, my reactant should start with a very high concentration, and over time, it is going to decrease. If I consider the products, remember that products are going to begin with a low or zero concentration, and they will increase until they reach an equilibrium position. So these are things that we have to just kind of be able to visualize, be able to think about, keep them in mind. Now, as our reaction continues, once again, our reaction concentration dips, our product concentration rises, and we're going to end up at an equilibrium position, which basically means the rate of the forward reaction and rate of reverse reaction are going to be the same. So here are a couple of additional examples of what we're talking about here. In this first example, again, concentration versus time, notice that once we hit equilibrium, the product values are greater than the reactant values. So I want to introduce a new term, just one of the bits of academic language that we use when we talk about equilibrium. When you have an equilibrium system and the product concentrations are greater than the reactant concentrations, we would say the products are favored at equilibrium. Okay, so in this case we have products being favored. In the graph here on the right, notice that as we reach equilibrium, our reactants are going to have a greater concentration than products. This tells us that our reactants are favored at equilibrium. So having this terminology in place, just understand what we're talking about. The equilibrium lies to the left means reactants are favored, or the equilibrium lies to the right, just think about the way the equation is written, would mean that products are favored. Now, what can happen once you have an equilibrium is there can be changes to the concentration of some reactants or other factors that can change the rate of reaction. So if you look at time zero, you'll notice that our nitrogen, hydrogen, and ammonia that are all parts of a chemical reaction sequence, what they're going to do is they're going to be horizontal, meaning that there is no change in concentration up until time 1. When we look at time 1, what we can see is there's a big spike in the nitrogen content. We increase or we add nitrogen to the system. As that nitrogen is introduced, notice now I have a surplus of nitrogen. It's going to react so that some of the nitrogen goes away in this reaction. The chemical equation that we're looking at, by the way, is the Haber process, which is nitrogen and hydrogen are going to react to form ammonia. So you'll notice that the reactant nitrogen is going to decrease at this point. Hydrogen is also, here our dashed line, that is also going to decrease. But our product will increase as I make that change. Here at time 2, you'll notice that we're going to make a couple of additional changes. We're going to increase the amount of nitrogen, increase the amount of ammonia, and increase the amount of hydrogen. This could be accomplished by decreasing the overall volume of our solution, assuming that these are all in gas phase. As these changes occur, what you'll notice is there are more moles of reactant on the reactant side compared to the moles of product. This will cause a shift in the direction that will produce fewer moles overall to get back to an equilibrium position. So here we see a decrease in nitrogen, we see a decrease in hydrogen, and an increase in the ammonia production. Finally, I get to another condition here at time 3. And at time 3, what ends up happening is we'll have an increase in nitrogen. So this is opposite of what's been happening. An increase of nitrogen happens. There's going to be a decrease on the ammonia, and there's an increase of hydrogen. One way that this could be explained, since you don't see a big jump, a big spike like this, is we're not changing concentration or volume. We might be changing temperature. In this situation, if you have this process and heat were a product, if I were to cool this system down, it would cause a shift to the left. If I were to heat the system up, it would cause a shift to the right. Actually, let's reverse that. The addition of heat causes a left shift. Taking away heat causes the right shift. So if I were to take away heat, once again, take it away, that causes a shift to the right and it would make more ammonia. When we look at it, we notice that the opposite is taking place and we're decreasing ammonia. So it must have been the opposite trend. We must have been adding heat at time 3. That addition of heat causes a shift in the left direction, meaning that we get a decrease of our products and we get an increase in our reactants. Now, hopefully you're getting an idea. We're going to talk in a lot more depth about this concept of how equilibrium will shift when you make changes. It's known as Le Chatelier's principle. But for now, just understand that if we make changes to the system, the equilibrium is going to change. The specific concentrations change. Now, one of the big misconceptions that my students have is they think that once you hit chemical equilibrium, there is no more reaction. It's as if the reaction has stopped. And on the large scale, it does appear that way. You don't see any additional color change. But you've got to consider that these molecules have energy. They're in motion. So on the microscopic scale, we've got to get this idea that if this is my process, I have A, going to be as my forward reaction? Well, if 10A are reacting in 1 minute to make B, 10B must be reacting in 1 minute in the opposite direction. So what's happening essentially is we keep having change, but in a set period of time, it's the same number of particles that are moving in a forward direction and a reverse direction. The one thing that I want to make sure you understand is we do not have equal concentrations at this point. It's the rate of forward and reverse reaction that are the same, not the molarity of reactants and the molarity of products. So do remember that at this point, you're going to have both reactants and products. They're going to find a ratio that is going to be stable at this specific point. And again, this is equilibrium, when the rate of the forward reaction is the same as the rate of the reverse. If the products and reactants have specific properties that we can see, for example, color, it makes it easier for us to identify where we are along the equilibrium scale. In this example, we have two different color expressions of our cobalt ion. On the left here, notice that we have our hydrated cobalt. It's going to have a 2+ overall charge for this complex. And what we're going to see is it's a light pink color when that's the primary species you have in solution. Well, this hydrated cobalt complex can react with chloride ions. The water would be removed, getting it away from this, and then you'll have a complex that forms with cobalt and the chloride ions. So these two different complexes shown in our square brackets are two different color expressions. We have the blue in our cobalt chloride, and then we have the pink with our hydrated cobalt. If you were to shift the equilibrium one way or the other, what you end up seeing is a purple color, indicating that we have a blend of the two expressions of the two ions. You can see both pink and blue, giving us our purple coloration. So hopefully this introduction to a dynamic equilibrium was clear, understandable, and we're going to be talking about this in much more depth as we move along.